So in previous lecture we have discussed about the wrist tracking voltage, and we have derived the relation of wrist tracking voltage and what is the peak value of wrist tracking voltage, and also we have derived the relation for rate of rise of wrist tracking voltage. So as discussed in the previous classes that this wrist tracking voltage is not uh, suitable for the circuit breaker, because once high wrist tracking voltage developed across the circuit breaker, then this will restrike the arc again, and second thing, this may damage to the circuit breaker. So we should avoid high voltage development due to the while opening up the circuit breaker contacts. So we must have some option to reduce this wrist tracking voltage. So there is one method which has been discussed here, that is called the resistance switching. With the help of resistance switching, we can reduce the magnitude of the wrist tracking voltage, or we can reduce the wrist tracking voltage so that the effect of the wrist tracking voltage will not hamper the operation of power system network. So as shown in the diagram, that we have a line network, that is inductance is represented by L. Then again we have a capacitor C which is connected with the line and ground, and this is the circuit breaker contacts. And again we have shown here that there is a fault which has been created, so line is grounded, here it is showing a fault, and once this fault is created, it means this capacitor C will be also grounded. So this whole capacitor voltage is connected across these circuit breaker contacts, and this is the E is the voltage, E is the input source. So as it is the same circuit diagram which has been described in the derivation of the wrist tracking voltage. Only thing is that we are here opting a method to reduce the wrist tracking voltage, so we have connected a resistance R across the circuit breaker contacts, so that during the high transient oscillation when developed across the circuit breaker contacts, a part of the current can be passed through the resistance to the ground, so that excess current flowing across the circuit breaker contacts can be avoided, and this will reduce the arc and arc voltage also. Now this resistance switching is connected with this sphere gap. What is this sphere gap? This sphere gap actuates when a sufficient voltage is built up across the circuit breaker contacts. So once this is actuated, it means the resistance R is automatically connected across the circuit breaker contacts. That's why here it has been shown that this is a sphere gap. So what had been told here in the resistance switching, that to reduce the wrist tracking voltage, a resistance is connected across the contacts of the CV. This is known as resistance switching. Since we are connecting a resistance across the circuit breaker contacts to avoid or to reduce the wrist tracking voltage, that's why it is called a resistance switching. Now the resistance is in parallel with the arc, and a part of the arc current flows through this resistance, resulting decrease in the current. So resistance is automatically switched in with the help of sphere gap. This already we have discussed. So this is what about the resistance switching. Now again we will derive the same type of relation, same type of differential equation as we have derived in case of evaluating the wrist tracking voltage. That will see here this current I which is flowing through this inductor L, that had been shown here that a part of current is flowing through this capacitor that has been denoted by IC, and a part of current which is flowing through this resistance that is denoted by IR. So what is total current I? I is equals to IC plus IR. Why? Because IR is the part of the current which has been bypassed through this resistance when sphere gap will actuate, and this resistance will be connected across the circuit breaker contacts. So by differentiating these currents, this will help out to derive the relation that how much resistance we will require to connect across the circuit breaker contacts so that we can avoid a restriking voltage, or we can reduce the magnitude of the restriking voltage. So let us see. We can derive the voltage equation. We can apply the KVL as we have applied in case of the restriking voltage derivation. That is L di by dt plus 1 by C IC dt equals to A. What is this? L di by dt plus 1 by C, same thing here iterated 1 by C, IC dt, IC is the current flowing across the capacitor C. So L di by dt plus 1 by C IC dt equals to E. This is the input source voltage. So this is the KVL applied again this circuit which has been written here. Again here E is taken as a constant because we have discussed that since a restriking voltage is very fast phenomenon, so we can be regarded as a constant. Now as in previous circuit, we have differentiated current that I equal to IC plus IR. So we can replace here that is in place of I, we have written di by dt. So in place of I, we can write IC plus IR. So we can write here L d by dt IC plus IR plus 1 by C IC dt equals to E. Again we can open up this circuit, this bracket. So we can write here L dic by dt plus L d by dt into IR, or d by dir by dt plus 1 by C IC dt. It is nothing but it is a voltage across the capacitor. So we can write 1 by C IC dt equal to Vc, and this is equal to E. Now we know that IC, current flowing through this capacitor IC, can be written as dq by dt. And what is Q? Q here CVC. So if you place d by dt and in place of Q we replace CVC, where C is the capacitance and Vc is the voltage across the capacitance. So we can write IC equals to d by dt CVC. Now if we differentiate this equation IC, so we can write here d by dt IC, that will be equals to C d2Vc by dt2. d2Vc by dt2. This is the equation second, this is the equation first, and after that we can see that what is the IR. Just see in the circuit diagram, what will be this IR? This IR will be nothing but it will be the voltage applied across these contacts and divided by resistance. So we can write IR equals to Vc by R. This will be IR. So same thing is written here, that IR equal to Vc by R, and we have differentiated this IR with respect to time t. So we have written dir by dt equals to d by dt and Vc by R, because equation is IR equal to Vc by R. Or further we can write 1 by R dVc by dt. This is the equation third. So we have derived the three relations, that is 1, 2, 3. Let us go ahead further. So from this equation 1, 2 and 3, if replace these values here in this equation, that is in this equation L di by dic by dt plus L dir by dt plus Vc equals to E. So if replace dic by dt here and IR, that is dir by dt with this value, so the equation first will become or can be written as this, that is the LC d2Vc by dt2 plus L by R dVc by dt plus Vc equals to E. Now if you take a Laplace transform of this equation, so we can write LC s square VCS plus SL upon R VCS plus VCS equals to E by S. Why E by S? Because we have taken E as a constant, that restriking voltage development is very fast, so E has been taken as a constant voltage source. So input is constant here. Now if you take a common VCS, we can write LC S square plus SL by R plus 1 equal to E by S, or if we take out LC also from this equation outside the bracket, so we can write LC VCS equal to S square plus 1 by RCS plus 1 by LC equal to E by S. So from this equation we can find out VCS. So what is VCS? VCS will be E by S and LC, and this term, that is S square plus 1 by RC into S plus 1 by LC. So for no transient, all roots of the above equation must be real, because we have to find the value of R so that the development of the restriking voltage or rate of rise of restriking voltage, this can be reduced to minimum value. So to ensure this, that there should not be any restriking voltage, that is the roots of this equation must be real, that is S equal to 0. So for this it is necessary that S square plus S by RC plus 1 by LC roots will be real if we can apply here that is the equation, that is the minus b plus minus b square minus 4ac upon 2a, that is the formula of finding out the roots of the equation. So we can write S equal to minus b, that is minus 1 by RC. From where minus 1 by RC is coming? This is A, B, C. Minus b means minus 1 by RC. Same thing written minus 1 by RC plus minus under root b square minus 4ac. What is AC? Just see here. What is AC in this equation? That is A is 1, that is A is 1 and C is 1 by LC. So we have written here, that is minus 4 upon LC, and by 2A. A is 1, so it will remain only 2. So this is the roots of the equation. Or further, if you derive this, then we can write S equal to minus 2 by RC plus minus root square 1 upon 2 RC ka whole square minus 1 by LC. So if roots are real, because if roots are real, then only we can avoid the restriking voltage. So a necessary condition for this, that roots should be real, that is this part be under root square part, that is 1 by 2 RC square minus 1 by LC. This must be greater than or equals to 0. This must be the condition which will be fulfilled. or we can write here 1 by 4 r square c square. This must be greater than equal to 1 by LC. So we can further simplify it that if we take out 4 this side here, so we can write 4 by LC should be less than equal to 1 upon r square and c square. Or further we can simplify, then we can calculate the value of r square. So what is r square? R square should be less than equal to LC upon 4C square. This is from this relation. Or we can write here the r square should be less than equal to 1 by 4 L by C. Or further it can be simplified. So value of r can be written as, that is r should be less than or equal to half and root square of L by C. So this is the value which is required to reduce the restriking voltage or to reduce the rate of rise of restriking voltage. That's why it is written here, if we select the value of r that is less than equal to half root L by C, then there will not be transient oscillation and the rate of striking voltage will be also reduced. So now in this figure we see that since roots must be real, so this part, that is under root square part, this must be real, that is this value must be positive. So to have this positive value, it means this 1 by LC part must be positive. That's why if you have the frequency of damped oscillation, so frequency of damped oscillations can be written as 1 by 2 pi root square of, that is 1 by LC minus 1 by 4 r square and c square. This can be written as, this is the frequency of damped oscillation. So we have discussed here in this lecture that what is resistance switching. Resistance switching means the value of resistance which must be connected across the circuit breaker contacts so that we can reduce the magnitude of the restriking voltage or the peak value of the restriking voltage or also the rate of rise of restriking voltage. So what is the value of R? Value of R should be less than or equals to half under root L by C. If you have this value, then restriking voltage can be reduced. So this was the overall lecture for the resistance switching.